Welcome back. So today's explainer is going to take us on a truly fascinating mathematical journey. We're venturing from the absolute unyielding order of geometry straight into the completely unpredictable nature of chance. Now, if you're preparing for the Cambridge IGCSE Math 580 syllabus, you already know that mastering the rules is key, right? But what happens when the rules themselves are trying to capture randomness? Well, strap in because we're about to find out.
Okay, let's dive right into our roadmap for today. First, the rules of transformation. Second, order versus chaos. Third, the pioneers of probability. Fourth, the probability scale. And finally, calculating the odds.
Section 1. The rules of transformation. Let's look at absolute geometric order. So we're starting our journey in a world where everything just makes perfect sense. A world where geometric transformations represent absolute, predictable mathematical order. Every single geometric mapping demands a rigid, perfectly predictable rule. Think about these 4 pillars of transformation. If you want to perform a reflection, you absolutely have to have a mirror line. For a rotation, you need a specific center of rotation and an exact angle. A translation? That requires a precise column vector to tell you exactly how far horizontally and vertically you're moving. And an enlargement needs both a scale factor and a center of enlargement. The point is, when you move a shape, say mapping square ABCD to a new position A', B', C', D', you're not just guessing. You are following a very strict mathematical recipe.
But let's flip that idea on its head for a second. If an object wxyz maps to an image w', x', y', z', how do you determine the inverse transformation to map it back? I really want you to think about that. Because the rules of geometry are so absolute, we can perfectly reverse engineer that mathematical order. If you know the exact rule you used to get there, you know the exact opposite rule to get back. There's literally zero guesswork here. It's total certainty.
Section 2. Order versus chaos and the limits of prediction.
But life and, advanced mathematics isn't always about total certainty, is it? We're now shifting away from that comforting certainty of shapes and vectors and stepping into the grander kind of philosophical reality of our universe. Back at the start of the 19th century, the French mathematician Pierre-Simon Laplace was convinced of something pretty incredible. He theorized that if you knew the exact position and velocity of every single particle in the universe, you could flawlessly predict the future. Why? Because everything was predetermined by scientific laws. It's almost like the ultimate geometric transformation. But, well, modern reality had a slightly different plan. Quantum mechanics and chaos theory came along and proved there are strict limits to ultimate predictability. The universe, as it turns out, just isn't completely predetermined.
Just take a look at this striking image of a massive swirling storm system. Chaos theory sits right at the center of understanding the limits of scientific prediction. When you're dealing with real-world systems that are this complex and unpredictable, you can't just slap a simple column vector or a mirror line on it to figure out what happens next. Because of the inherent chaos of the real world, mathematicians realized they needed a completely different framework to handle the unknown.
Section 3. The pioneers of probability and the study of chance.
So to tame this inherent randomness, mathematicians created theoretical probability. And this absolutely did not happen overnight. Let's walk through how some historical titans evolved the study of chance. Back in the 1600s, Blaise Pascal and Pierre de Fermat started writing letters to each other. What were they talking about? Not the deep fate of the universe, but actually problems connected to games of chance. Then, in 1657, Christian Huygens wrote the very first book on the subject, beautifully titled The Value of All Chances in Games of Fortune. Jump ahead a bit to 1821, and we have Carl Friedrich Gauss working on the normal distribution. Over just a couple of centuries, these brilliant thinkers took simple parlor games and turned them into the incredibly complex statistical models that rule our world today.
And here is one of those main architects, Blaise Pascal. I just think it's truly amazing to humanize this highly abstract math by realizing that Pascal's casual letters back and forth with Fermat effectively birthed the formal study of probability we use right now. I mean, they were literally just trying to figure out how to win at gambling.
Section 4. The probability scale and the likelihood of events.
All right, let's bridge this fascinating historical context directly into the practical rules of your Cambridge syllabus. The crucial point you need to know is this formula right here. Theoretical probability equals the number of favorable outcomes divided by the total number of equally likely possible outcomes. This simple, elegant little fraction is the engine behind all theoretical probability. A favorable outcome simply refers to the specific event you're looking at actually happening, while the total possible outcomes refers to, well, all the different types of results you could possibly get. And because it's a fraction grounded in reality, it has very strict boundaries. On the probability scale, if the probability equals 0, it implies the event is entirely impossible. No way it's happening. On the flip side, if the probability equals 1, it implies the event is absolutely certain to happen, guaranteed. Every single event of chance everywhere must fall somewhere on this exact scale between absolute impossibility and absolute certainty.
Section 5, Calculating the Odds. Let's see probability in action.
Let's shift from those abstract formulas into a really concrete, practical example. This brilliantly illustrates how we plug the reality of an ordinary fair dice directly into our formula to calculate distinct probabilities. Say the event is rolling a 6. How many favorable outcomes are there? Just one, getting that single 6. But the total possible outcomes? There's 6 of them. Rolling a 1, 2, 3, 4, 5, or 6. So your final probability is 1 over 6. Pretty straightforward. What if the event is rolling an even number? Well, our favorable outcomes are 2, 4, and 6, so that gives us 3 favorable outcomes. The total possible outcomes remain 6, so the probability is 3 over 6, which we easily simplify down to 1/2.
But, we also need to account for what doesn't happen. These are known as complementary events. The rule is incredibly simple. The probability of an event not occurring is 1 minus the probability of it occurring. So if the probability of rolling a 6 is 1/6, the probability of not rolling a 6 is simply 1 minus 1/6, which gives us 5/6. Understanding this relationship between an event and its complement is an absolute game changer and a massive time saver for your calculations.
So, we've journeyed all the way from the strict predictable rules of geometric transformations to predicting the likelihood of the unknown using fractions. But I want to leave you with this final, kind of provocative thought. If theoretical probability gives us a perfect mathematical fraction, why does chance guarantee that theory rarely perfectly matches practice in the real world? Think about that the next time you roll a dice, or honestly, just look at a weather forecast. Mathematics gives us the framework, but the universe, it always keeps just a little bit of its chaos. Thank you so much for joining me on this explainer. Keep studying, keep questioning, and I'll catch you next time.